Right, next. Set of notes in Schoology, energetics and mechanisms of solution formation. Again, notes provided for you, and you can go ahead and use your own or use the ones I provide. All right, so just a reminder, when we talk about solutions, we are talking about homogeneous mixtures, and it means that the solute is dispersed uniformly through the solvent. So the question is, how does that happen? What is that process like, and what is the energy related to it? All right, well, we know that matter in nature has a natural tendency toward mixing, okay? It is a spontaneous process, which we'll get to later on in the trimester, because it increases the disorder, right? The particles are together with their own kind, and now they are mixed together, so it's more disordered. We know that things in the universe tend toward disorder because it lowers the energy of the system. So things in the universe will tend toward lower energy. Okay, so if you have two chemicals and the particles are free to move about, they will mix. Okay, it happens naturally. Okay, however, we know that the materials around us don't just all mix together. If not, we would become part of the matter around us, and the matter around us would become part of us. So, what keeps things from mixing? Well, physical barriers and IMFs. Those are what are needed to prevent mixing. All right? So, in order to mix, what then has to be true is that the IMFs between the solute and the solvent particles have to be close or greater in strength than both the IMFs between the solute and solvent particles and the solvent particles. Okay, so in other words, the IMFs between the things that are mixing, the solute and the solvent, have to be greater than the solute all by itself and the IMFs in the solvent all by itself. So what determines whether a solute and a solvent will solvate each other? Well, we kind of alluded to it a little bit and by saying that the IMFs that form have to be the same strength or greater than the IMFs that existed in the pure solute or the pure solvent. Chemists use the axiom, like dissolves like. We talked about this a little bit when we were doing the What's in the Bottle lab, okay? So we know that because of that, polar substances tend to dissolve in polar solvents, and nonpolar substances tend to dissolve in nonpolar solvents. Or more specifically, things that have some kind of charge or partial charge will dissolve in things that have charge, and things that do not have charge tend to dissolve in things that do not have charge. This leads to substances either being soluble or insoluble in a particular solvent. It also lends its weight to two liquids being miscible or immiscible. In other words, liquids mix or don't mix. Okay. So again, like dissolve likes comes from this idea that the more similar the intermolecular attractions, the more likely the substance are to be soluble in one another. For example, glucose, which has some hydrogen bonding, is very soluble in water, while cyclohexane is not. Okay? Cyclohexane is all carbons and hydrogens, so there's only dispersion forces, whereas glucose has OH groups, which make hydrogen bonding possible, and so therefore they will dissolve in a water molecule. Okay? So what is the barrier here? Well, if we think of this as being three processes. One, the solvent particles have to spread out, the solute particles have to spread out, and then they have to mix together. Our issue here is that the forces holding the water solvent together are much, much greater than the forces holding the cyclohexane together. And so as a result of that, the cyclohexane cannot get the water molecules apart in any way, shape, or form. These want to stay together, and so as a result of that, they don't separate the cyclohexane. Okay. Here's another one. Vitamin A is soluble in nonpolar compounds, but not water. Vitamin C is soluble in water, but not fats. Okay, so let's think a look at this again, okay? So vitamin A is soluble in nonpolar compounds, but not water. So because vitamin A only has one polar group down here to interact with the water, and most of it is nonpolar, that means that the forces in the vitamin A are not strong enough to pull apart water molecules and create space. Okay, vitamin C has the opposite problem. Okay, it's soluble in water but not fats. Again, it has lots of polar groups to interact with the water. Okay, but in terms of a fat, fats are nonpolar. So as a result of that, the vitamin C sticks to itself much better than it will stick to the fat molecules. And as a result of that, it has no incentive to pull apart. All right, last thing, gases in solution. Things like carbon dioxide and soda and things like that. In general, the solubility of gases in water is going to increase with their increasing mass. Okay, and the reason for that is larger molecules tend to have stronger dispersion forces. So you eventually get to a point where the IMFs in those large molecules are big enough that they will start sticking to the water better than they stick to each other. So as a solution forms, then the solvent pulls the particles apart, solute particles apart, and then it surrounds them or solvates them. Okay, so it pulls them apart and then it mixes them together and surrounds them, gets around them. There's our solvation happening again. Okay. So if an ionic salt is soluble in water, it is because the ion dipole attractions are strong enough to overcome the lattice energy of the salt crystal. So in other words, if our lattice energy is very, very, very strong, it's going to be unlikely that we're going to be able to have something where we have the water particles being able to pull it apart. All right, so that's sort of the physical nature of it. What about the energy changes in the solution? Well, simply put, three processes affect the energetics. How much energy does it take to separate the solute particles? How much energy does it take to separate the solvent particles? And how much energy is released when we mix them back together? So the overall delta H of the process, the enthalpy change in the process, depends upon the delta H of each of these steps. Okay, separating solute particles, so pulling things apart, that's going to require us to put energy in, so it's endothermic. Same thing, solvent, getting the solvent particles separated a bit is going to require an input of energy, so that's going to be endothermic. And then the particles are going to form new attractions, and anytime we form new attractions, in this case between the solute and the solvent, energy gets released, and that is exothermic. In this example that we have over here on the left, the energy required to separate the solvent plus the energy required to separate the solute is an increase of energy from the beginning up to here in our energy diagram. And then the energy that's released when they mix releases more energy than those two energies to separate things. Okay? In this particular case, the overall energy is lowered. This is a spontaneous process. It just happens. All right? Things do not tend to occur spontaneously unless energy of the system is lowered. Yet we know in some processes, like the dissolution of ammonium nitrate in water, heat is absorbed, not released. This is a classic chemical reaction where if we put ammonium nitrate into water, it cools down, and so it's oftentimes what is used in chemical cold packs. Okay? Well, if it feels cold, it's endothermic altogether. In other words, the energy required to separate the solute and the solvent is more than the energy that is released when they mix back together. So the question then is, if this is a situation where the energy at the end is more than the energy at the beginning, why do endothermic solution processes just happen, right? You would think we would need a constant input of energy for that to work. Well, there's another piece to it. Okay, we don't just get energy lowering from the energy released from the mixing process. There's also a lowering of energy due to the disorder or new randomness of the system. This is something we call entropy. And again, it's something we'll get into more in one of our future units. But what gets us the rest of the way? What gets us the rest of the way is disorder, lowering energy due to disorder, which we call entropy. So as long as the enthalpy change overall is only mildly positive, entropy can get us the rest of the way to lower energy. So even though the overall enthalpy may increase, the system of the energy can still decrease if the system becomes more disordered, which is what happens when we dissolve things. That's it for this set of notes. See you next time.